Yeah, but I mean, we have to, I mean, frankly speaking, I'm not so sure. I mean, of course, I'm also much interested in the phase transitions and them at all, like even this ultra-thin limit, whether they will be the same as we see them in bulk. It's another topic which we are also quite interested. Besides,
actually,
I mean, like,
yeah, actually, the sodium orthoferrite sample, that's exactly on this phase transition where you have this reorientation from A to B axis. So, you know, if these type of things, you can also, you know, make samples, and you can, if you're interested, look at ultra-fast dynamics of that. You know, we're happy to share samples.
Yeah, great. I'll keep this in mind. You just need a little bit to calm down so we can basically deliver results from your field.
No worries, we have enough on our platter, just an offer. But anyway, I think
offer is like it's super cool. I'm very happy with it. More than.
Now I'll hand back to Libor because now he's got to rumble.
Yes. So we are soon to start, maybe in 1 minute. Okay, can you see guys my screen? Very good.
Yeah, looks fine. Well, we see not full screen, we see the PowerPoint. We don't see the full screen. Yes, now it's perfect.
Okay, very good. Okay, so we have a free. So let me start today's seminar from the online series, which is organized by SPIN Interdisciplinary Center Phenomena and by SPIN+X. So from the SPIN Phenomena Center, it's of course its director Jairo Sinova, and from the side of SPIN+X, professors Martin Eschliman, Burkhard Hillebrand, and Matthias Kloy, who we see is present among the panelists. And my name is Libor Šmejkal, and I will be today moderating the seminar on behalf of Professor Sinova because he is traveling. So you know the format. So we will have also after the talk some questions from the Zoom attendees. I will promote them to panelists so they can ask the question in person, or I can just read the questions. And today it's a great pleasure to have a speaker, Dmytro Afanasiev, who is assistant professor at Radboud University in Nijmegen. He obtained his PhD in 2016 from this university, and he is interested in ultrafast phenomena, ultrafast magnetism, and light-induced phase transitions, as you will see from his talk. And also, I just learned on Twitter that he just freshly got his ERC starting grant. So with this, let me give the floor to Dmytro, and we are looking forward for your talk.
All right. Just a moment. So, my screen. Can you see my screen? Yeah.
Yes, very nice.
All right. So many thanks for this beautiful introduction. So I'm very glad to attend this seminar, which I was actually attending many times just as a guest. I mean, like just watching many speakers, and today I got a chance to be a speaker essentially. So I would like to thank Jairo, first of all, for inviting me to give this talk. Also, using this occasion, I would like to thank Matthias for organizing this and for all the other organizers of this beautiful seminar session. I also like to thank, by the way, for a beautiful gift which I received from the SPICE. I like it a lot. Many thanks, and thanks for Elena for helping to organize all of it. But all right, let's now come back to science. So today, title of my topic is light-driven antiferromagnetic magnonics. And in the course of this talk, I'll try to show you how light in a form of ultra-short pulses is able to excite ultra-broadband wave packets of coherent antiferromagnetic magnons. But before going into magnetism and into operating with magnons, I would like to start from the very basics which we are all familiar with. And namely, I'd like to start with electrons. and their usage as a data carrier. It's something what we encounter in our everyday's electronics. So we widely use them in regular life. But at the same time, we also know from physics, from electrons, that electrons, they have a dual nature. So they're at the same time particle and they at the same time wave. And we're actually dealing with particle-like transport of electrons as we transport information from electricity, even from point A to point B. And so if you talk about particle-like transport of electrons, we talk in terms of mass, charge, velocity, we talk about electronic collisions. But naturally, electron being a wave should support the wave-like transport. So as you can see from this figure, electrons should be able to carry information from point A to point B, as what you can see from this droplet on the surface of the water. But if you talk about waves, about wave-like transport, we basically operate with a different notation. We talk about wavelengths, we talk about frequency, we talk about dispersion, we talk about group and phase velocity. And even the way how two electrons should interact, it will be interference and diffraction. So it's very much different from a particle-like transport. But in fact, mainly if you talk about electrons, we basically talk about them as about particles, because there's a limited manifestation of wave-like nature of electron in regular life. And this is because electrons are characterized by low coherence. And what I mean is they are characterized by very short momentum scattering time, which is on the order of 10 to 20 femtoseconds. So within this 10 to 20 femtoseconds, electron propagates as a wave. It propagates in a ballistic fashion. However, after this time, it typically experiences a collision. And you cannot anymore talk about electrons as about wave. You should start talking about electrons as about some diffusive particles. And that leads to the fact that electrons are characterized by also very short mean-free propagation paths, which is on the order of 10 nanometers. So basically only on this time scale and on this length scale, you can talk about electrons as about waves. And another thing, that this low coherence, it leads to enhanced dissipation, and as a consequence, to very strong heating. So all the electronics of today is suffering from heating, and we would like to fight against it. And essentially, we are very happy. We are very lucky, because electron is not the only quasi-particle in the world, which is characterized, which has a dual nature of particle and wave. There's basically many others. Some of them are collective, some of them are rest excitation, some of them bosons, some of them are fermions. So you can see as a phonons, plasmons, and one of them essentially is magnons. And what's special about magnons? That basically they are highly coherent quasi-particles. And let me show you. So magnons essentially are waves of a spin or spin waves. Magnons essentially are waves of spin angular momentum. And they emerge in magnetically ordered media. It can be ferromagnets, can be antiferromagnets, and they basically support the propagation of such a waves of angular momentum. So they are essentially the waves. And what's important, they're characterized by very long coherence times. So these times can be more than 1 millisecond. Just compare 1 millisecond to 10 femtoseconds. There's basically dramatic difference in coherence of electrons. They also very much, they essentially, as I say, they are low dissipative. They can maintain their spatial coherence over distances more than 1 millimeter. So essentially, these are really, really macroscopic distances. They're at the same time, they're scalable. You can bring down their wavelengths to less than 10 nanometers. And another thing, what is also very much important if you talk about magnons, that they are highly nonlinear particles. And the price for this nonlinearity essentially is relatively cheap. And nonlinearity is something what is crucial if you would like to perform computing using, for instance, magnons. Essentially, these advantages have been recognized long time ago, as there exists a whole discipline which studies magnons. And this and like for the purposes of wave-based transport and data processing with magnons. And this discipline is called magnonics. And magnonics within the last 20 years has reached a tremendous progress. So you can actually design logic gates. You can create even some devices for analogous data processing. Even magnon transistor has been shown how to realize. So it's just fantastic progress. And actually, like if you think about future, many people think that magnonics should develop in insulators. People even talk about spin insulatronics, where you can, and that's just main idea, just to get rid totally from electrons, to get rid of all these charge carriers, which are very highly dissipative, which leads to increased heating. So just to realize pure spin-based information and communication technologies. And all of this in insulators, which simply lack electrons, where the electrons are localized. And it's interesting, if you look up on a family of magnetic insulators, you basically find that most of magnetic insulators are not ferromagnets to which you are used to. And essentially here I have to say, so ferromagnets basically material, I think you all know these materials which are characterized by non-zero net magnetization. So all the spins are pointing either up or down. In fact, nearly all the materials are essentially antiferromagnets. Antiferromagnets are very much similar to ferromagnets, but they're characterized by two interpenetrating magnetic sublattices, and they work in such a way that there is a no net magnetization in total. At the same time, material is characterized by magnetic ordering. And there exist two magnonics nowadays, ferromagnetic magnonics, which basically a lot of advances has been done within 20 years, and antiferromagnetic magnonics, which remains so far almost totally unexplored. And let me show you that antiferromagnetic magnonics has a very, very strong appeal for the case of very fast and very efficient devices. So if you compare antiferromagnetic magnons to ferromagnetic magnons, you will find that antiferromagnetic magnons are characterized by significantly higher frequencies than ferromagnetic magnons. So typically, antiferromagnetic magnons operate in the terahertz frequency range, while ferromagnetic magnons operate in the gigahertz frequency range. Moreover, antiferromagnetic magnons are characterized by very high spin wave group velocities, which typically lie on the order of tens of kilometers per second. And what's also very much important, only antiferromagnets support non-dispersive propagation as a consequence of a linear light-light dispersion. So this dispersion of antiferromagnetic magnets is basically intrinsically linear, and it's very much different from the ferromagnets, where dispersion is intrinsically quadratic. So what does prevent us from using antiferromagnets, prevent us from realizing high-speed antiferromagnetic magnonics? And actually, the fact is that something what makes them unique, so this terahertz frequency, makes them very hard to use. Because in the conventional ferromagnetic magnonics, traditional source of coherent spin wave excitation is actually a current. So what you do is here you can see a strip line along which you send current. This AC current is this AC current produces RF magnetic field, and you resonantly couple this magnetic field to spin wave, so you get emission out of your material. But the problem is these sources, they typically operate in the frequency range less than 50 gigahertz. And for higher frequencies, radiative losses just simply become unbearable. So you really cannot exploit these traditional sources in antiferromagnets, which typically features frequency on the order of 1 terahertz. And it has been really, really a long puzzling whether basically what we can know about antiferromagnetic spin waves, because simply no means to excite these spin waves. And here I would like to describe one experiment which have been done recently, where people actually finally were able to realize spin wave transport in antiferromagnets. So what people have done, they used actually a spin accumulation as a local excitation of magnon density, and then propagation of this density towards some distances, where it has been shown that actually in the antiferromagnetic magnons can propagate over macroscopic distances as well, and these distances can reach up to 10 micrometers. But as a problem that this spin accumulation, it basically creates some diffusive accumulation and diffusive propagation of magnons. So in such sort of experiment, the coherent nature of magnons is not really revealed. You still consider magnons as a quasiparticles, as a particles rather, which propagate from the source. So we don't know still about phase, we don't know about frequency, we don't know about group velocity of the magnons which propagate. So we essentially are not exploiting the main advantages of antiferromagnets, so their high speed and high frequency. At the same time, there exists a discipline which for many years develops in parallel with antiferromagnetic magnonics and with magnonics itself. It's basically a discipline which is called Antiferromagnetic optospintronics. In this discipline, people use ultra-short optical pulses to drive coherent spin precessions in antiferromagnets. So what you do, you basically use a very strong pulse and very short pulse, which is typically on the order of 100 femtoseconds. And with this pulse, you excite antiferromagnet and you just drive some spin precessions. And you can track the spin precession directly in the time domain. So you do time-resolved experiments. For this, you use another weak probe pulse for which you can measure different properties. You, for instance, can measure second harmonic, you can measure polarization rotation, you can measure emission of terahertz. And here's basically examples of what people typically obtain in such sort of experiment. So here I plot polarization rotation, so one which you can see also here, as a function of time delay. So at the moment 0, you get excitation. And then directly in the time domain, you study material response. And this material response, if you excite spin waves, very often it looks like some oscillations. These oscillations, they basically represent spin precession. So what I would like to show you here, that you can see excitation and evolution of the spin excitations with light, with ultra-short optical pulses directly in the time domain. And typically, you also are able to control phase of such spin precessions. You also can drive spins to very large amplitudes, which are typical on the order of several degrees. You can even achieve a reversal of magnetization of spin orientation. So basically, potential of ultra-short optical pulses is very high. And just to describe you how it works, it essentially, without going deep into the details, the main mechanism behind is the following. The ultra-short optical pulse can be seen as a pulse of effective magnetic field. And being very short in the time domain, so as short as 100 femtoseconds, so you realize a really impulsive excitation. This pulse is very broad in the frequency domain, with a bandwidth which can exceed 10 terahertz. And if you think about this 10 terahertz, it's basically a really large number. With such bandwidth, you can, in many antiferromagnets, you can excite spin waves across nearly the whole brilliance zone. So isn't it amazing? But a problem that in practice, people which are dealing with such optical excitation of magnons, they're typically driving only zone center magnons with a k vector equal to 0. So basically, the full potential is not realized, just simply because the zone center magnons, they are basically lowest frequency magnons. They do not really also support very often propagation. It's just because this dispersion is hyperbolic, so it's quadratic close to k equals 0. So you cannot use such magnons for the sake of propagation. And this is simply to understand why the reason is just because there are some limitations of light, because there exists a very large linear momentum mismatch between the driving light wave and a spin wave. So simply, velocity of light is several orders of magnitude higher than that of spin wave. And so as a consequence, you can drive only the zone center magnons. But as you can see, it's not really much use of these magnons for the case of creating of antiferromagnetic magnonics. And that's the reason why actually this light-driven excitation of spin waves and antiferromagnetic magnonics, they for long have been developing in parallel, but it is very limited cross-fertilization. One way to solve this problem would be to localize the optical excitation by confinement. What you do in this case, you create a very inhomogeneous, non-uniform excitation. And this inhomogeneity serves as a source of finite k vectors, with basically bandwidth limited by the way you can focus your light, for instance, you confine your light. And one way to do it, for instance, is just to use tightly focused beams. But the problem is that here you have a limitation, again, which comes from the light, from light nature of your pulses. You are simply diffraction limited. And also you are able to realize such excitation in ferromagnets, in antiferromagnets, which are characterized by very high frequencies. To propagate relay excitation, you need to have spin waves with a wavelengths on the order of 100 nanometers. So you need to make a confinement on the order or even less than 100 nanometers. And we actually were thinking about how to make such excitation. And we came up with the idea that why don't we use actually some natural properties of materials? Why don't we use absorption of material? Because if you use in order to, and that all to create sub-wavelength localization of the spin excitation. So the idea is the following: you use light frequency, so the photon energy of which is tuned in resonance with highly absorbing electronic transition. And being highly absorptive, this transition actually leads to a very strong attenuation of light, such that the whole light excited area can be limited to a nanoscale actually within the absorption profile. So essentially you create something what is similar to a skin depth. And essentially in such a way, and this, as you can see here, it can be brought down to less than 100 nanometers. So in such a way, you create strongly non-uniform spin excitation within the area on the order of 50 nanometers. So you create, in some sense, nanoscale terahertz spin wave antenna, which should lead to emission of broadband spin wave packet. And as you can see here, as this inhomogeneity of this excitation is very strong, it should serve as a source of many k vectors, so of very broad bandwidth. All right, and being driven by this idea, we actually were looking for material which should be very sensitive to optical excitation. And we actually put our attention on dysprosium orthoferrite. This material is very well known for so-called optomagnetic effect. So you can easily, simply speaking, you can easily excite spin precession in this material with the help of ultra-short pulses of light. Just let me show you that, for instance, you can drive spin precession in this material invisible with a visible light. You can do it with near-infrared light. You can do it even using mid-infrared pulses of light, and even with a fine infrared light, so with a strong terahertz pulses, you are able to drive spin precession in these materials. It's also antiferromagnetic. It has a relatively high Néel temperature, so antiferromagnetism in this material is very strong. So it's basically also room temperature antiferromagnet. And our idea was, all right, if all this spectrum has been already studied, let's just try to approach UV range. And let's try to pump and excite spins in this range and to see whether we basically are able to drive spin wave emission of propagating coherent magnons. Let me tell you why this UV range is special for dysprosium orthoferrite. So here I show optical absorption, and what you can see that the photon energies about 2.5 electron, band gap absorption starts to basically onset of the band gap absorption starts up, and it rapidly grows with the photon energy. So essentially, and that leads to increase of the absorption coefficient, and at the same time, it leads to increase into the decrease of the penetration depths of light. So for the photon energy of about 3 electron volts, this penetration depth is already 50 nanometers. So it basically means that you can create, by pumping your material with a photon energy of 3.1 electron volts, you can create strongly non-uniform excitation with a characteristic length of 50 nanometers. And this is essentially was the idea of our experiment. Let's just try to use such specially, let's just try to use such ultra-short light pulses with a photon energy of 3.1 electron volts, which should provide such non-uniformity. And let's try to drive spin waves. But one problem is to, one problem is to drive the spin waves. And totally different problem is basically to see the spin waves, to see propagating excitations optically. And to see them, we employed 2 types of Magneto Optical effects. The first one is Magneto Optical Faraday effect. So Magneto Optical Faraday effect is the following. So to see changes, so that's basically change of the light polarization plane upon propagation through a magnetized media. And so Faraday effect operates in the transmission, so it's a bulk sensitive. So you are able to be sensitive to some basically properties which emerge across the whole thickness of your sample. But as we are dealing with near surface excitation, we employed a different effect also, basically Magneto Optical Carrier effect, or MOC. And this effect is basically, it's similar to Faraday effect. It's also rotation of the polarization plane, which is proportional to magnetization in media. But now it basically works in reflection. So this effect is surface sensitive. So basically we have now 2 means to probe bulk and to probe surface, or let's say near surface. And let me show you our results. So we first started with the Faraday effect, and Faraday effect has been employed for many times in dysprosium orthoferrite and many other orthoferrites as well. So what we see here some oscillatory dynamics on a time scale of several tenths of picoseconds. And essentially, like as I say, you basically in many of such time-resolved experiments, we see oscillations, and these oscillations, just by looking to literature, we can attribute to some spin precession. And that corresponds to the spin precession at the zone center. So it's just like in literature, you can find the basically frequency of 175 terahertz, which you can see here as a Fourier transform. It just perfectly matches. So with the Faraday geometry, we are probing k equals 0 magnons. That's no surprise. Now let's have a look for the Kerr geometry, for the MOC experiment. So what we see here, we again see coherent oscillations. So there's a very clear sine waveform. But if we now look to the Fourier transform, we actually were very much surprised first to see, because also excitation is the same. The frequency of these oscillations is totally different. It's basically substantially higher. It's more than 50 gigahertz higher. So one way, basically, it immediately tells us that the Faraday effect and Magneto Optical Carrier effect, they provide us access to different, qualitatively different dynamics of spins. And one way to imagine what can be the reason for this would be to say, what if MOC effect is probing non-uniform magnetic, so some non-uniform spin precessions, so with a k not equal 0. So, and that's natural, because frequency is higher, so that would basically match the dispersion relation. We looked a little bit more into this dynamics and compared Faraday and Mach effect. So what we have done, we basically started to vary pump photon energy. And for low photon energies, there is basically no absorptions. So you can say that below 2.4 electron volts, sample is nearly, basically absorption is nearly zero. So the excitation is very uniform. And what we see, when excitation is uniform, Faraday effect, so amplitude of this wave, which you see via Faraday effect, it shows a very large amplitude. Well, so once we start to increase the photon energy, and once we enter this region of strong absorption, while Faraday effect goes down, so the amplitude of the excited wave here goes down, what we see in the Mach, it basically starts to grow. So again, what we see, the Faraday and the Kerr effect, they show different sensitivity to the uniformity of the light excitation. And what we see is the Mach actually really needs your excitation to be strongly non-uniform. So how do we understand? So what do we probe this Mach? We just know for the moment that they probe different dynamics of spins. And just to understand what we probe with Mach, let's now have a look on the essentially process which we are dealing with when we are measuring Mach. And this process actually includes three waves. It includes the incident wave, a reflected wave, and also the spin wave, which propagates away from the surface. So basically, we have a three waves interaction. And if you consider three wave interactions, you should fulfill momentum conservation for these waves. It basically means that you efficiently probe with Mach only spin waves, which are defined by the probe wavelengths. So varying probe wavelengths, you should get sensitivity to different spectral components. Let me show you this again. So here I plot spin wave dispersion in dysprosium orthoferrite. So you can see frequency, you can see wave vector, so wave number basically. And here I probe with which wavelengths we are probing the spin waves. So this is all about the Magneto Optical Kerr geometry. So probe wavelength is 660 nanometers. And this would correspond to a spin wave with a wave number 4.2 10 to the power 2 microns, inverse microns. So if you plot it here, what we get, the frequency is slightly above 0.2 terahertz. And that's exactly what we are probing in our Mach experiment. So just to show you a little bit more, as I say, we are exciting not a single propagating spin wave, we're actually exciting broadband spin wave packet. It basically means that it has a spectral density for different wave numbers. So it's basically many waves excited simultaneously. And so here you see basically Fourier image of the spin excitation. And just by varying the probe wavelengths, you actually can map out, you basically get access to different spectral components of the spin wave. You can even basically map out the dispersion of this material. So they perfectly lie on the theoretical dispersion of this material. Let me now a little bit tell you what these waves are and what their properties are. Essentially, if you plot velocity as a function of wave vector, you will find that their group velocity is on the order of 12 kilometers per second. And that's actually really, really a lot. It's nearly 2 times more than the sound velocity. So they are dealing with the supersonic waves, supersonic spin waves. It basically means that their propagation is even faster than the limiting speed of at which heat propagates. We also can estimate lifetime of these spin waves, which is on the order of 85 picosecond. And knowing their velocity, we can estimate coherence length. And so this coherent length is on the order of 1 micrometer. Again, we are dealing with some nearly macroscopic distances. So far, I have been talking about spin waves in dysprosium orthoferrite. But recently, we extended this research to some other orthoferrites because this family is very broad. We essentially studied holmium orthoferrite. We also studied samarium terbium orthoferrite. And in both these materials, we found that this soft UV excitation is able to drive these coherent propagating waves. And I would like to here to stress out that in holmium orthoferrite, just varying the probe wavelengths, we were able to map out a wave packet of coherent spin waves with a bandwidth which is on the order of 0.2 terahertz. All right, now a little bit about excitation mechanism. I have to be straight with you and say that we are still not fully sure about the excitation mechanism. So it was very much surprising to us to get a little bit understanding of this mechanism, because we thought as we are pumping strongly absorbing transition, this excitation of spin waves should be intrinsically non-thermal. Oh, sorry, I beg your pardon. So it should be intrinsically thermal. But in fact, we tried to rotate the pump polarization plane with respect to the spin orientation. And what we observed, also upon this rotation, absorption doesn't really change. The amplitude of the wave basically is changing. So you can basically make a wave having phase either 0 or pi, which I denote here in plus and minus. And this is very much resembling so-called inverse Couton-Mouton effect. So when light actually works as or serves as an instantaneous magnetic anisotropy, which deflects spins from their respective equilibria. But it's still puzzling that excitation in the strongly absorption region can be intrinsically non-thermal. All right, so I'm left with 10 minutes, and I would like to tell you a little bit some information about actually the spin wave packets. So I hope I was able to convince you that with light you can excite broadband spin wave packets of coherent antiferromagnetic magnons, and the bandwidth of these magnons can be as large as 0.2 terahertz. But as a question, so you excite a lot of spin waves. Question: can these spin waves interact within the wave packet? Can they interact with some other quasiparticles? And this question we wanted to answer. So this data is not really published, so please take it rather as a first glance. So let's have a look now on our data which we obtained in dysprosium orthoferrite. Here I plot Fourier transform of k equals 0 mode, so of the uniform spin precession, and k not equal 0. What we see that the line width of finite k magnon is significantly more narrower than that of uniform spin precession with k equals 0. And this is which means that the damping of finite k mod is significantly smaller than k equals 0. And it's actually puzzling, because higher energy magnons you have, it basically means it has more scattering channels as a consequence higher damping. But in fact, we see opposite. We see that the 0k should have it has actually a larger damping. So we were puzzled by this, and we performed some experiments in which we studied this k equals 0 mode. And what we have done, we basically varied energy of our pump. So we started with 1.9 electron volts, and what you can see here, I plot absorption profile. So 1.9 electron volts, this absorption is very negligible. So material is nearly transparent. So you do not really excite any finite k excitations. You just are able to excite only k equals 0 mode, so only uniform precession. And what we see that here damping actually of this k equals 0 mode is very low. So it can live more than 300 picoseconds. But once you start to increase the photon energy, the damping actually goes down. And at the energy of 2.8 electron volts or 3.1 electron volts, it becomes really, really strong. And this essentially in this region, absorption is very high. And there we actually create the spin wave packet. So what we shown that you are basically able, just by changing the pump photon energy, you are able to change damping of k = 0 mode basically by nearly 2 orders of magnitude, and increasing the laser fluence, you can even suppress it more. So basically, we found a way how you can control damping of k = 0 mode. So how do we understand it? So if you talk about damping, the immediate thing which comes to mind, what's the origin of spin wave damping? And that's several mechanisms which are very well known. That's basically two magnon scattering, like spin magnon scattering, phone magnon scattering, and also magnon phonon scattering. So it's all about scattering. And let's now have a look on a magnon photon scattering. And I'm talking, so far, I was not really talking about phonons, but in fact, when you pump your excitation in the region of strong absorption, you are not only exciting magnons, which can be seen here as such a ripples, high frequency ripples on top of lower frequency, slower mode, so lower frequency oscillations. And this actually, just trust me, these oscillations are basically phonon mode. And this is really no surprise, because when you pump in absorption region, you basically expand your material locally, and such expansion leads to emission of acoustic phonons. So this is basically what's known in literature as picosecond acoustics. And we also, the same way as we map out phonons, we can also map out dispersion, the same way if we map out dispersion of magnons, we are able to map out dispersion of phonons. So here basically, what is important, what's the important takeaway here, that we're exciting not only magnons, but also phonons. And another important thing is that by reconstructing these dispersions, we see there is no direct coupling between magnons and phonons. And so only one way that magnons and phonons couple, that would be basically a 3-particle process. That basically would mean that you have a one magnon which basically merges together with phonon into another magnon. But a question, why do we see it only for k = 0 mode? An explanation is also relatively simple. There is some very strong energy and momentum constraints for such a magnon-phonon coupling. First of all, you have to conserve energy and you have to conserve momentum. But as their group velocities of magnons and phonons are very different, you can fulfill this only below some critical k vector, which is on the order of 2 to the power 2 inverse micrometers. So basically only in this region, the scattering occurs. So such a scattering, when energy is transferred from such a low k mode to higher k mode assisted by the phonon. And that basically explains, and the frequency of this magnons is very close to F0. So very close to such a uniform k = 0 magnon. All right, so I'm nearly done. Let me just tell you some outlook. So I have briefly mentioned that antiferromagnetic magnons are characterized by linear dispersion relation. And this linear dispersion relation is also very much unique. So light is characterized by linear dispersion. Some relativistic particles are characterized by linear dispersion and dispersion relation. And basically what it means, that it supports non-dispersive propagation, which basically means that such a propagation when velocity does not depend on frequency. It basically means if you somehow create a wave packet of coherent magnons of some shape, they would propagate in the antiferromagnetic media without the changing shape. So the very same, essentially, what ultrashort optical pulses do. So you create terahertz wave packet of photons, and then you can use such ultrashort optical pulses to excite spins, for instance. But at the same time, you can create, so in this way, in terms of as waves, antiferromagnetic magnons are not much different from wave packets of spin waves and antiferromagnets. There's basic terahertz wave packets of magnons, and you can create ultrashort spin wave pulses And the dream would be to interconvert ultra-short optical pulses into ultra-short spin wave pulses. All right, let me summarize. I hope I was managed to show you. I hope I managed to show you all optical excitation of a broadband wave packet of coherent propagating antiferromagnetic magnons. We verified this mechanism in a broad class of orthoferrites, and we see some preliminary fingerprints of many body interactions within such light-driven magnon wave packet. And I believe that our discovery lies the ground towards a new all-optical platform for broadband coherent antiferromagnetic magnonics. Last, I would like to acknowledge people who took part into this research, particularly Andrea Caviglia and his group. So particularly Jorit Hortensius, who led this research, and Matthias Mathiesen, as well as our collaborators from Lancaster University in the group headed by Rostislav Mikhailovsky, our collaborator from Kiev, Boris Ivanov, Roberta Citro, and a big thank to Alexei Kimele. So, and as we end, thank you very much for your attention, and I'm very, very much open for all your questions.
Okay, thank you very much, Dima, for a super interesting talk. So now we have a series of people who want to ask a question. So let me start with Gilles. I will promote two panelists. So let me see. Yes, you can ask the question. So you need to switch.
Sorry, can you hear me?
Yeah.
Yes, now we can hear you.
Yeah, thank you. Thank you for a nice talk. So you have measured the group velocity of AFM spin waves around 12 kilometers per second. So as far as I know, that this value is in the same order of some ferromagnetic spin waves. So my question is quite simple: that how to efficiently increase the velocity of AFM spin waves? Thank you.
Thank you for your question. So, in fact, as I say, like ferromagnets, they're characterized by quadratic dispersion. Essentially, higher k vector you take, larger the group velocity you get. But in fact, antiferromagnets have a linear dispersion, and their speed is already the maximal one. And the way to increase this speed, so this velocity, is just to increase Curie temperature. Because at the very end, these waves are driven by exchange interactions. So if you increase TC or TNL, that's the way to go.
Okay, thank you.
Okay, let's go for the next question from Sumit.
Yeah, thank you for this wonderful talk. We are actually doing some theory on the same line, and I have some questions regarding that. So first question would be, could you comment on the effect of temperature in the antiferromagnetic magnon? I mean, I'm more interested in the noise. So can I see this smooth let's say well-defined magnon frequency in finite temperature, or it would be screened with the noise?
Well, I mean, I would say, I mean, I don't know how to answer this question correctly. So we are dealing with coherent magnons. So their amplitude is way more larger than that of thermal magnons. So typically we are dealing with like a deflection of spins on the order of 1 degree. So I'm not so sure whether you can see it with temperature. They're significantly like orders of magnitude lower. So I'm not so sure whether you really now experiment, like, but if you really stick to our experiments, that I can address your question about temperature. I think it should matter. And in fact, we don't see, like, we see this excitation, but we see this excitation, like, I mean, like for the case of experiments which I described, only for the temperatures below than 100 kelvins. So in fact, also, we were looking for room temperature propagation. We do not really see it yet. And that might be also sensitivity of our setup or really effect of temperature, but temperature does something. Okay. So apparently, maybe you get some sort of like thermal population of magnons. And then our coherent excitation starts to compete with thermal population. But that I cannot really say. So
okay.
We are still into it.
Okay, great. Another question would be, does your system has a significant spin orbit coupling?
Good question. I'm not so sure whether it matters for the excitation, but our system does has a very strong spin orbit coupling, and the reason for this is the presence of 4F ions. So basically, iron itself has a very big spin orbit coupling, but it basically imparts some orbital momentum from dysprosium ions and also from holmium. So I mean, effectively, as this dysprosium is exchange coupled to iron, you can say that it does have.
Okay. I mean, the reason I'm asking, because as much I understand, theoretically, spin orbit coupling would be the main channel to transfer energy from laser to the spin system. But at the same time, it will enhance the damping of the system. That means your magnon will die faster. So what would be the exact role of spin orbit coupling? Do we need a stronger or weaker to create long-lasting magnon optically?
That's a good question. The fact that we essentially, like you ask it in the right way. So indeed, so the fact that we're able to control phase of the magnon, it clearly indicates that excitation proceeds via spin orbit channel. But about damping, I'm not so sure. I think there exists some other channels of the damping which would kind of suppress, I mean, would increase it way more. And I think like spin orbit here is not really the most dominant. At least that's my assumption.
Okay.
I think just this many body interactions would basically contribute significantly more.
Okay, that would be all. Thank you.
Okay, thanks for the very nice questions. So let's go to the next question from Professor Alexandra Kalashnikova.
Yes, hello, Dima, thank you very much for the really beautiful presentation. I have a question, maybe it's a little bit technical. So you mentioned that the speed of the spin waves which you excite is larger than the sound waves, but it's and they both are finite with respect to the speed of light. So in experiments with the excitation and probing from different sides, could you really see this delay in time when this optical and when phonons and magnons arrive? So could you see these delays?
Well, we never realized experiments when we excite from both sides, and that's mainly because it's a very interesting experiment and a very interesting suggestion for the experiment. And I think we would see some delay between this magnon and phonon also excitations. But the problem is that, like, if you really want to realize such experiment, your samples should be very thin, on the order of like 1 micrometer, because otherwise your waves would simply die out.
Okay.
So I mean, I think that, I mean, it's some way. For instance, I think like I just before the lecture, before the presentation, I talked to Matthias Chloe, and he says that basically in yttrium orthoferrite, the propagation length should be on the order of 10 micrometers. So that sounds like a little bit more feasible to try this contra-propagating magnons to collide them. But definitely, I think it would be some delay. Yeah.
Yeah, and if I may just another short question. So how do you exactly detect phonons in your experiments? Is it also via the same mechanism, like this Bragg reflection as for the magnons?
Yeah, it's the very same way. They typically appear. I mean, this, frankly speaking, it's very in our experiment, it's very hard to get rid of them. So you rather need to adjust conditions to not see them.
Right.
So you always excite them, but once you enter the absorption, but it's only if you operate in the reflection geometry.
Okay, thank you.
But I mean, like the way we detect them is the same way as spin waves. With spin waves, we see off-diagonal components of the dielectric tensor modulated by spin waves, and with phonons, we see the diagonal components.
Okay.
Matthias, do you want to react to this point?
No, just a different question.
Okay, so in that case, thanks for the discussion, and let's go to the next question from Professor Gisela Schitz.
So thanks for this very nice talk. I have a question. To investigate waves, there is a little bit more than to measure the frequency and to know that's k equals 0. Is there any chance to see these waves really propagating and also to measure something like an absolute amplitude? you see only the frequency. Something is moving, but waves, you want to look how they propagate, how they survive over domains, walls, and so on.
Yeah, that's essentially, at least for now, to me, it would be a dream experiment. Something that I hope we would be able to realize. But one way to do it essentially is so if you so far we're able to excite them to propagate only along in depth.
Yeah.
So one way would be to do it. It's the way as Alexandra suggested. So essentially to make a collision experiment from two sides, or it's a one way. And another one, what we are thinking, you need to break this translation symmetry of space in the plane. And what I mean is that you need to make one way to go, or at least would be to make a nano patterning of your sample.
Yeah, for
instance, to make grids, and that's something what we are actively studying now. So we want to see emission out of such a patterned structures.
Yeah.
So that of course, I mean, of course, one drawback of all our experiments is the fact that we see them in the reciprocal space.
Yeah.
And a dream would be to see in real space.
Yeah, for sure. So thank you.
Thank you.
Thank you. Now let's go to a question by Matthias.
Yeah, thanks, Dima. Super exciting talk. I have a question. So you showed that in this material, you have these supersonic magnons. So the magnon velocity, i.e. the slope of the dispersion relation is higher for the magnons than for the phonons. I mean, I was under the impression that's a generic feature of antiferromagnets that have sufficiently high exchange. Or do you know materials where this is opposite, or where you can tune it to make it faster or slower?
Yeah, thanks for your question. I mean, in principle, that's what you expect from antiferromagnets, that their group velocity is just higher. But I mean, you just simply go, you can go to low temperature antiferromagnets. For instance, if you take a yield temperature on the order of like 50K, basically, I think you can even cross them. So you can even really realize a direct coupling.
But yeah, I mean, there's not so much, I mean, it's a bit tough to tune the exchange constant on the fly. I mean, you need to have the right material and so on. No, I mean, yeah, absolutely. But I think it has to, what I have to say, to be frank, that would be a study of a single material. I think tuning is a bit complicated. Maybe just by doping. Maybe like if you would basically make a doping, can you somehow make your material like a dilute antiferromagnet? That could be a way
make
to
the
go.
exchange really weak until it kind of caves in. But then you have to do a low temperature meassure, which is a pain.
I mean, another way potentially would be that I just started to think that you can. I'm not so sure whether it will work, but maybe just application of magnetic field might help there.
So which orthoferides have a low nail temperature? So we
I think they all have the very high. It's 600 kelvins for all of them.
Okay.
But in principle, it can be some other materials. Again, I think orthoferides is just like a model system which we knew and where we could easily distinguish these features.
All right, great, thanks.
Thanks, Matthias. So following this question, what would be the ideal material which would be tunable by the magnetic field? What are the main parameters? So the band gap, I guess, plays a role.
Yeah, that's true. I would say a little bit different way. I think the ideal material to drive these spin waves actually would be material with zero anisotropy. And that's just because if you have anisotropy, your dispersion becomes hyperbolic. So it's kind of like it becomes quadratic at small k vectors. But if you take a material with a very low anisotropy, then basically you really get this linear light-like dispersion. And then you can utilize all your excitations. And for instance, a good candidate for this would be, let's say, iron borate. That's a material which is an easy plane antiferromagnet. And it's a very, very small, so it's an easy plane antiferromagnets, where actually anisotropy in the plane is very, very weak, so you can freely rotate spins, I believe.
And in terms of the numbers which you were showing for the orthoferides, how far are you in the Brillouin zone in terms of percentages?
Why it's still small. I mean, like it's you can compare, let's say, 50 nanometers to less than 1 nanometer. So it's like 1/50 still. Unfortunately, we cannot go more so far. But there is a way to do it, and one way, of course, like would be to create confinement which is even less than 50 nanometers. So in principle, if you would be able, for instance, there might be emission from antiferromagnetic domain walls, which are on the order of like 10 to 20 nanometers. And that would serve as a source of emission.
So do you see some fundamental principle limit, how far in the Brillouin zone you could go with this?
I would say if you take heterostructures of two different antiferromagnets, there's basically no limit. That will be just a single unit cell. But it's just, I mean, a question whether you will be able to detect these magnons. That's a different question, but the awareness would be not, I believe that will be not really limited.
Okay. Very interesting. So let's see. I don't see any more questions. So once again, thank you, Dima, very much for all these interesting slides and also for very interesting and educational discussion. And yeah, I'm looking forward to meet you somewhere at the conferences. Here I'm stopping the stream.
Right. Thank you very much, guys. Also, it was a great pleasure. Bye-bye.
Thanks, Dima. All the best.
Thank you. Bye-bye. Stay in touch.
Take care, everyone. And,